Moving forward, we'll talk about diverging sequences, sequences that diverge. And we did an example in the last video where we showed something was divergent by essentially showing it can't converge. So if it can't converge, it must diverge. So when we start thinking about writing infinity as a limit of a sequence, we're not saying that the difference between the terms a sub n and infinity becomes small as n increases, because it's becoming larger. And we're not asserting that there's some number of infinity that the sequence approaches. We're merely using this notation to capture the idea that a sub n eventually gets and stays larger than any fixed number as little n becomes large, as that index value becomes large. So, and if you look at the pictures over here on the right of the screen, they kind of illustrate what we're thinking about. So looking at the definition, the sequence a sub n diverges to infinity if for every number m, right? So here we have an m value. There is an integer n, so there's an n over here, such that for all values, for all index values n which are larger, so n, little n is somewhere off here, larger than that chosen value n, that the terms become greater than this number m. They're above that line. And if that holds, we can write our limit in this way or in that simpler notation. The limit as n approaches infinity of a sub n equals infinity, or just a sub n arrow infinity. So similarly, we could say it goes to negative infinity if there exists a number n, and we're using m here on the bottom as a little m as our value, right? Because it's negative or below the x-axis. So we're saying a very small value as opposed to capital M in the above picture, a very large value. So for every small m value, there exists an integer n that for all of the indices past n, we have terms that are below that lowercase m value. And so in that situation, we would say it diverges to negative infinity. So we kind of understand divergence now, and we'll talk about calculating limits of sequences. So since sequences are functions with a domain restricted to positive integers, limits rules are similar. So these three rules should look really similar to our sum, difference, constant multiple, and product rule, quotient rule for limits. So the limit of a sum, right, if we're doing the lim of these sequences, it would be each of those output values. We can subtract the values if it's a difference. If it's a constant multiple, that k can come out in front. This limit of a product is the product of the limits, and then the same for the quotient as long as that denominator value doesn't equal 0. Okay, so these should make sense. We're just finding the limits for sequences. So let's do an example. So we're going to illustrate how we can use these properties here for sequences and finding their convergent value. So one thing that we know is the limit as n goes to infinity of 1 over n is going to equal 0. We showed that in a video, the previous video to this. So what we're doing here is we're just going to try and use these properties to break it down in a way that I can figure it out. So in a sense, this is the same as writing the limit as n goes to infinity of 5 times 1 over n times 1 over n. All right, so I've separated these sequences here. And this, the constant multiple, can come in front, and then the limit of a product is the product of those limits. So I can say the limit as n goes to infinity of 1 over n times the limit as n goes to infinity of 1 over n. And of course we know that this is going to go to 0 and this one goes to 0. So we end up with 5 times 0 times 0, which equals 5. Further, we'll just do one more. We'll do the limit as n approaches infinity of n minus 1 over n. So this is the limit as n goes to infinity. If I unadd, I get n over n minus 1 over n. Or rather, the limit as n goes to infinity of 1 minus 1 over n, which we can then say is the limit as n goes to infinity of 1 minus the limit as n goes to infinity of 1 over n. The limit of a constant is just going to be that constant, and the limit of 1 over n is 0, so we end up with 1 here. Okay, so using these properties in this theorem, we can simplify the limits into smaller pieces that allow us to figure out the limit of the sequence. Our next theorem is the sandwich theorem for sequences. So if we have a sequence a sub n, a sequence b sub n, and a sequence c sub n, they all consist of real numbers. If b sub n is sandwiched between all of the points for a and c, then it holds that as long as the limit of the sequence A matches the limit of the sequence C, giving us L, then the one in the middle, sequence B, must also go to L. Okay? So if the sequence bounding it on the bottom and the sequence bounding on the top converge to the same value, then the sequence that's in between them must also converge to the same value. So we're going to do a problem here. We're going to show that 1 over 2 to the n approaches 0. And one thing that we need to make sure we keep in mind that we know is that 1 over n approaches 0, right? And 1 over n is larger than 1 over 2 to the n, because if I let n be just, 1, 2, 3, 4, etc., I would have 1, 1/2, 1/3, and 1 to the 4th. And if I do the same with my n values for 1 over 2 to the n, I would get 1 over 2, 1 over 2 squared, 4, 1 over 2 cubed, 8, 1 over 2 to the 4th, 16, right? And so in all of these situations, when I line up those corresponding first, second, third, and fourth terms, these values are smaller than the other values, right? So what we can say here is since 0 is less than 1 over 2n is less than 1 over n, and the limit as n goes to infinity of 0 is equal to the limit as n goes to infinity of 1 over n, those are both equal to 0, then what we know in the middle, we can say the limit as n goes to infinity of 1 over 2n must also equal 0 because it is sandwiched between the other two. So it's really a simplistic solution here, but sometimes you have to get creative with choosing your sequence that would be larger or smaller. So now we'll talk about another theorem, the continuous function theorem for sequences. So we will let the sequence a sub n be a sequence of real numbers. And if a sub n approaches this value L, and if a function that is continuous at L and defined for all of the terms in the sequence, then the function of the sequence equals the function of the limit. So we can plug the limit into the function. Okay? So let's do an example. I have two examples in here for this theorem. So we're going to show that the square root of n plus 1 divided by n approaches 1. Well, we'll think about this as like being a composition, right? So we have the square root of x, and we plugged into that x n plus 1. So the radicand, what's under the radical, n plus 1 over n approaches 1. And we did this in a previous similar example from a previous video. So we can show that this approaches 1. All right? So what we can think about here is we can take this and we'll say let f of x equal the square root of x. And the L value we want is going to be 1. So then the square root of this radicand, n plus 1 over n, would equal the square root of that L value I have right here, 1. And that is equal to 1. So there's my final answer. All right, moving on, we have just one more example talking about continuous functions. So we want to show that this converges. So we'll show that 2 to the 1 over n converges. So we're going to start, again, we go back to a sequence convergent value that we know. And so something that we know is that 1 over n, that sequence, approaches 0. And I see that 1 over n right here, 1 over n, is in my original sequence. So the way we can think about this is I'll say, well, let a sub n equal 1 over n. And we know for that this limit is 0. So if we let f of x be 2 to the x, then f of 1 over n is 2 to the 1 over n. And then by our definition, that needs to equal the function evaluated at that limit, which is 0. So this would be 2 to the 0, and 2 to the 0 is 1. So moving ahead, again, when we talk about sequences converging, we say that these are really similar to limits. And one of the properties we used to help us with limits was L'Hopital's rule, right? So we use L'Hopital's rule a lot. And what L'Hopital's rule says for limits is if you have something in an indeterminate form, such as 1 over 0, right? So, or, x x over 0, or 1 to the infinity. These are all different types of indeterminate forms. And if we have an indeterminate form, one thing we know we can do is we can find that limit value by taking the derivative of the top and the derivative of the numerator separately. So if we define that sequence as a function, so this function is defined for all x values greater than your n sub 0, and that a sub n is a sequence of real numbers such that the sequence can be represented as a function. Then the limit of the sequence is L whenever the limit of the function is L. So really we're just going to treat this sequence like a function. Okay? So we're going to show as an example here that the limit as n goes to infinity of the natural log of n over n equals 0. So since ln x over x is defined for all x which are greater than or equal to 1, then we can treat this, instead of being as n goes to infinity, that sequence, we're going to treat it like a function, and we'll say the limit, I'm going to use x, as x goes to infinity of ln x over x. So applying L'Hopital's rule, that's the same as saying the limit as x goes to infinity. The derivative of ln x is 1 over x, and the derivative of x is just 1. So this becomes the limit as x goes to infinity of 1 over x, and we've seen that several times already today. That is 0. So at this point, some of you are probably going, well, how am I supposed to know what to do, when to do, how to apply what property? And really the only way I can tell you that is with practice. But we do have some commonly occurring limits that we know. We like to kind of store them in our Rolodex of limits for these sequences that we can figure out. So you can see them all here. We've got the limit as n goes to infinity of ln n over n, which is what we just did, is always going to be 0. We use that one a lot. The limit as n goes to infinity of some nth root of n is going to equal 1. The limit of x raised to the 1 over n power is going to equal 1 as long as your n is as long as your x is positive. All right. If we're dealing with x raised to an n, that's always going to go to 0 as long as the absolute value of x is less than 1. So that means we're dealing with something that has to be a fraction, like 1/2 in there. The limit as n goes to infinity of 1 plus x over n to the n is going to go to e to the x. Euler's number being an exponential expression. And then the limit as n goes to infinity of x to the n over n factorial equals 0 for any x value. And so, for formulas 3 through 4, those all had an x in them. 3 through 6. As long as x remains fixed, x is a constant value, some number, then these hold. Okay? So I have a few examples in here. If we wanted to show convergence, say natural log of n squared over n. So we can rearrange that, and that would be 2 ln n over n, which we know from our chart up here is going to be 0. So 2 times 0, we end up with just 0. Or nth root of n squared. Well, that's the same as writing n to the 2 over n, or n to the 1 over n squared. And so this piece, 1 over n to the 1 over n, that's the same as what we're looking at, for example, 2, which that becomes 1. So this is the same as saying 1 squared, or just 1. So we use like a little bit of algebra to manipulate these so that we can figure them out. C here, the nth root of 3n. That looks very messy. The nth root of 3n, that's the same as saying 3 to the 1 over n times n to the 1 over n. And both of those are going to go to 1. So we get 1. Negative 1/2 n. Well, that is like formula 4 from up above. So as long as it's a fraction, it could be negative, but it has to be fractional. We can say that that's going to approach 0. E, if we have the sequence n minus 2 over n to the nth, unadding that, that's 1 minus 2 over n to the nth. And that is like formula 5 up above, so that becomes e to the negative 2, because 2 was my x value. And lastly, for f, 100 to the n over n factorial would approach 0 using formula 6. And I know this video is getting kind of long, but we have one last topic in here to talk about. And these are functions defined recursively, recursive definitions. So considering what we've talked about so far, each sequence has been directly, all of the terms in the sequence have been calculated directly by plugging in your index, 1, 2, 3, 4, 5, etc. But sometimes sequences can be defined recursively, and what that means is we use a previous term in the definition of the sequence. So sometimes we're going to be using the value of an initial term or the values of initial terms, and then we create a rule called a recursion formula, and this allows us to calculate any later term value from a term that precedes it. A term that came first is used to determine the term that follows it. All right, so we have an example here. I've got 3 of these. So if we think about the sequence, 1, 2, 3, 4, etc., 5, going on, this can be defined recursively. And what we could say is we'll let a sub 1 equal 1. So thinking about this, what would a sub 2 be? If we wanted to use a previous term, basically we're adding 1 to the former term each time to get the next term. So a sub 2 is a sub 1 plus 1. A sub 3 is a sub 2, which is 2 plus 1. A sub 4 is the previous term, a sub 3, which is 3 plus 1. So that allows me to create a recursive term here, recursive sequence, a sub n equals the previous term, a sub n minus 1 plus 1. All right, another example. Let us consider 1, 2, 6, 24, all the way to some n factorial terms. So these are being determined as factorials. And for example, 3 factorial would mean 3 times 2 times 1, which is 6. And you'll see that 6 is my third term here. Okay, so this factorial sequence could be defined recursively. And the way I can say that is we are going to let a sub 1 equal 1. That's my first term. So then a sub 2 is 2 times a sub 1. A sub 3 is 3 times a sub 2. A sub 4 is 4 times a sub 3. Because, and it's easier when we look at this with larger numbers. This is my fourth term. A sub 3 was found by doing 3 times 2 times 1. So 4 times 3 times 2 times 1 is 4 factorial. Okay? So if we want to create our method for finding our recursive term, that would be n, whatever your term you're dealing with, times the previous term, because it's the factorial of all of the other terms preceding it. So a sub 10 would be 10 times a sub 9. And we'd have to continue making this list and figure out what a sub 9 is. And then the sequence of Fibonacci numbers. So Fibonacci numbers, 1, 1, 2, 3, 5, 8, 13, keeps going. So Fibonacci numbers are sum of the previous two numbers. So in this case, in order to determine this, we're going to start with two n values. We're going to say, well, we need to let a sub 1 be 1 and a sub 2 be 1. So in this situation then, a sub 3 is a sub 2 plus a sub 1. A sub 4, which is 3, is a sub 3 plus a sub 2. A sub 5 would be a sub 4 plus a sub 3. So if we look at our fifth term, my fifth term up here is 5. My fourth term is 3. And my third term is 2. So we've got 5 equals 3 plus 2. So this makes sense. And the way we might define this would be a sub n plus 1, the following term, equals a sub n, the term which would be immediately before that, plus a sub n minus 1, which is the term immediately before a sub n. All right, and we will stop with that for today.